Picture this. 50 million years ago, the landscape of what is now South Asia looked nothing like it does today. Instead of crowded cities and dry plains, the region was a lush, tropical world. Thick forests covered the land, and shallow seas crept far inland. The air was hot, heavy, and humid, buzzing with insects, the calls of early primates, and the rumbling footsteps of strange, hoofed mammals. Among these animals, near the banks of rivers and coastlines, prowled a predator about the size of a wolf. It had long legs, sharp teeth, and probably looked more like a dog or a jackal than anything you'd recognize as a whale. But hidden inside its skull was a secret, an adaptation that revealed where its descendants were heading. The structure of its inner ear bones was specialized for hearing underwater, a trait that no other land mammal had. This creature, known as Pachycetus, is the starting point of our story. Over the next 50 million years, Pachycetus's descendants would leave the land behind, step by step, generation by generation, until they had become the masters of the oceans, the whales we know today. And the scale of this transformation is almost impossible to imagine. The largest land animal alive now, the African elephant, weighs about 6 tons. The largest whale alive today, the blue whale, can weigh 180 tons, 30 times larger than an elephant and bigger than even the mightiest dinosaurs. How could evolution achieve this? How does natural selection take a small, wolf-like mammal and turn it into a creature longer than a basketball court, able to dive to depths greater than 10 feet than Mount Everest is tall, and capable of singing across entire oceans? That is what we're going to explore in this episode. But before we dive into fossils and species names, let's set the stage by imagining the world in which this evolutionary drama unfolded. We're talking about the Eocene epoch, roughly 56 to 34 million years ago. At that time, Earth was warmer than today. There were no permanent ice caps at the poles, meaning sea levels were much higher. Tropical and subtropical forests stretched across regions that are temperate today. Crocodiles and palm trees thrived as far north as what's now England and Canada. The oceans were full of strange creatures. Giant sharks, primitive seabirds, and early relatives of modern fish swam alongside animals that would look alien to us today. This was an Earth bursting with diversity, but also an Earth in transition. Mammals, which had been relatively small and obscure during the age of dinosaurs, were beginning to radiate into new forms, experimenting with new lifestyles. Some mammals took to the skies as bats, some became giants like the brontotheres and rhinoceroses, and some, just a few, began to return to the water. Now, here's an important fact to remember. Whales are mammals. They breathe air through lungs, not gills. They give birth to live young. They nurse their babies with milk. And they are warm-blooded. This means that despite their ocean lifestyle, whales are more closely related to animals like cows, pigs, camels, and hippos than they are to fish or sharks. In fact, DNA and fossil evidence shows that their closest living relatives are hippos. This might sound surprising. After all, hippos spend a lot of time in water, but they are still unmistakably land mammals. Yet when paleontologists looked closely at whale fossils, they found ankle bones with the same distinctive structure as those of hippos and other even-toed hoofed mammals. This was the smoking gun linking whales back to their land-dwelling ancestors. The fact that we know this story so clearly is thanks to one of the best fossil records of any major evolutionary transition. From land mammals like Pachycetus, to amphibious swimmers like Ambulocetus, to fully aquatic forms like Basilosaurus, the step-by-step transformation is preserved in stone. Each fossil is like a snapshot, a chapter in the story of how evolution works over millions of years. And it's this fossil record that makes whale evolution one of the most compelling examples of evolution we have. You can hold a Pachycetus skull in one hand and a dolphin skull in the other, and see the changes. Nostrils migrating toward the top of the head, teeth shifting in shape, ear bones adapting for sound underwater. Evolution is not a theory written in books. It's written in the bones themselves. So, to really understand whales, we have to walk this journey step by step through the key transitional species. In the next part, we'll meet the walking whales, animals that could still roam on land, but were already beginning to hunt in water. They're not just evolutionary curiosities. They're the living proof of how life reshapes itself, adapting to new environments and new challenges. From here, we'll see how legs shrank, tails grew, nostrils shifted, and entire lifestyles changed. By the time we reach modern whales, you'll see just how radical and how beautiful this transformation really was. Now that we've set the stage, let's meet the first real characters of the whale story, the walking whales. These were animals that still spent much of their time on land, but were beginning to dip their toes, quite literally, into aquatic life. Our first stop is with Pachycetus, which lived about 50 million years ago in what is now Pakistan. Fossils of this animal show us a predator that would have looked a lot like a dog or a wolf. It had long legs, a long snout, and sharp teeth. At first glance, you might not recognize it as a whale at all. But here's the giveaway. Its inner ear bones were specialized in a way unique to whales. This single feature connects it unmistakably to modern dolphins and blue whales alike. Imagine Pachycetus prowling the banks of a river, snapping at fish that swam close to the surface, or chasing small mammals along the shore. It probably hunted both in water and on land, making it an opportunistic feeder. This dual lifestyle makes sense. Many evolutionary stories begin with generalists, animals that can thrive in multiple habitats. Over time, those flexible traits get refined into specialization. But Pachycetus was only the beginning. Just a few million years later, its descendants gave rise to one of the most extraordinary transitional animals ever discovered, Ambulocetus natans. Ambulocetus means the walking whale that swims, and the name could not be more accurate. Picture an animal the length of a crocodile, with short, powerful legs ending in webbed feet. Its body was elongated, its snout full of sharp teeth, and its tail likely helped it undulate through water. Unlike Pachycetus, Ambulocetus wasn't very good at running on land. Its legs were too short and its body too heavy, but in the water, it was perfectly at home. Fossil evidence suggests it used its hind limbs in a paddling motion, much like modern otters or seals. Over time, its spine became more flexible, hinting at the eventual shift to tail-powered swimming that defines modern whales. One of the most fascinating details about Ambulocetus comes from its skull. The placement of its nostrils was beginning to shift upward, not yet a blowhole, but the first step toward one. This subtle migration tells us that evolution was already solving the problem of breathing efficiently while swimming. Its ears also reveal secrets. The bones of Ambulocetus were heavy and dense, which would have helped it hear underwater by reducing the distortion of sound waves. Today, dolphins and whales are masters of underwater acoustics, and here we see the very beginnings of that ability. But let's pause for a moment and really appreciate what this means. If you were standing on the shores of an Eocene river and saw an Ambulocetus lumbering into the water, you might not immediately think, that's a whale. And yet, genetically and anatomically, that's exactly what it was. It was a creature in between worlds, too awkward to be fully terrestrial, but not yet fully aquatic. This in-between lifestyle raises an important evolutionary question. Why make the leap to water in the first place? The answer lies in opportunity. During the Eocene, rivers, lakes, and coastal seas were teeming with fish, invertebrates, and other prey. For a predator like Ambulocetus, the water was an all-you-can-eat buffet. Natural selection favored those that could swim better, hunt longer underwater, and spend more time in aquatic habitats. Over generations, these traits accumulated, pushing whales further and further from land. Think about seals and sea lions today. They give us a living snapshot of what life may have looked like for these early whales, creatures that could still haul themselves onto land to rest or give birth, but which depended more and more on the ocean for survival. The difference is that seals stopped halfway, keeping both lifestyles. Whales, on the other hand, would go all in. After Ambulocetus, the fossil record shows a clear progression. One particularly important discovery was Rhodhocetus. This species lived about 47 million years ago and represented the next big step toward a fully aquatic whale. With Rhodhocetus, we see shorter, sturdier legs that were even less useful for walking on land. Its tail was more powerful and its body more streamlined. Paleontologists believe Rhodhocetus swam more like a modern otter or seal, relying on its tail and webbed feet. But here's the detail that really blew the case wide open: the structure of its ankle bones. These bones, called the astragalus, had a distinctive double pulley shape, the same structure found in modern even-toed hoofed mammals, also known as artiodactyls. This group includes hippos, camels, pigs, and deer. The connection was undeniable. Whales weren't just any mammals, they were part of the artiodactyl family, and their closest living relative today is the hippopotamus. This discovery was a turning point. Before then, scientists debated where whales fit into the mammal family tree. Some thought they might be related to carnivores. Others guessed at different hoofed mammals. But the ankle bones of Rhodhocetus settled the argument. Whales are hoofed mammals that abandoned land for the sea. So let's recap this incredible sequence. Around 50 million years ago, Pakicetus lived on land but hunted near water. By 48 million years ago, Ambulocetus could swim and walk, straddling both worlds. By 47 million years ago, Rhodhocetus was mostly aquatic, with shrinking legs and a powerful tail. In just a few million years, a blink of an eye in evolutionary terms, whales had gone from wolf-like hunters to creatures that could no longer live without water. What's most amazing is how complete this fossil record is. We're not looking at guesses or missing links. We're looking at a chain of animals that show each stage of transformation in vivid detail. Every time a new fossil was discovered, it filled another gap, making the story clearer. This is why whale evolution is often used in textbooks as one of the best examples of macroevolution in action. And this is only the beginning. Because after Rhodhocetus, whales would take their boldest step yet, becoming fully aquatic. They would lose their legs, grow massive tails, and begin to resemble the whales we recognize today. Their bodies would become streamlined, their nostrils would migrate to the top of their heads, and their size would begin to increase dramatically. In the next part of our journey, we'll meet one of the strangest whales of all, a 50-foot-long serpent-like creature that swam the Eocene seas, a creature with tiny, useless legs and a body built for a life it could never have imagined on land. By around 41 to 35 million years ago, whales had crossed a point of no return. They were no longer creatures of two worlds, like Ambulocetus or Rhodhocetus. They had become fully aquatic. Their legs had shrunk, their tails had grown powerful, and they had lost almost all ability to walk on land. The fossil record from this period introduces us to some of the most remarkable and bizarre creatures in the whale lineage, the Archaeocetes, or ancient whales. Among them was one of the strangest and most iconic, Basilosaurus. Despite its name, which translates to king lizard, Basilosaurus was not a reptile. Early fossil hunters who discovered it in the 19th century mistook its long, eel-like body for that of a marine reptile, but closer study revealed it was a mammal, and not just any mammal, but a whale. Let's imagine Basilosaurus in its prime. This was a true giant of its time, reaching lengths of 50 to even 60 feet. Its body was elongated and serpentine, much longer and thinner than modern whales. Instead of the smooth, rounded shape we associate with dolphins and blue whales, Basilosaurus looked almost snake-like, slithering through the ancient seas with side-to-side undulations. It was a predator. Its skull was over a meter long, filled with sharp, serrated teeth. Unlike the fish-trapping teeth of earlier forms, Basilosaurus had molars designed for slicing flesh. Fossil stomach contents tell us it preyed on large fish and even smaller whales. Imagine the oceans of the Eocene, these long-bodied monsters cruising the seas, hunting anything they could overpower. But the most fascinating feature of Basilosaurus is something much smaller: its legs. Fossils show that this massive animal still had hind limbs, tiny, useless for walking, but present nonetheless. Each leg was only about 30 centimeters long, compared to a body many meters in length. These legs were far too small to support the whale on land, but they weren't completely pointless. Some scientists believe they may have been used as claspers during mating, helping males and females align their bodies in the water. These tiny legs are a perfect example of a vestigial structure, a leftover from an evolutionary past. They remind us, in bone and fossil, that whales once walked on land. Even today, modern whales carry echoes of these ancient legs. If you X-ray a dolphin's skeleton, you can sometimes find tiny pelvic bones buried deep inside its body. Evolutionary ghosts of limbs long lost. Basilosaurus wasn't the only ancient whale of its time. Another important genus was Dorudon. Unlike the giant Basilosaurus, Dorudon was smaller, about 15 feet long, and much more similar in shape to modern whales. It had a shorter, stockier body, flippers at the front, and a tail fluke at the back. Unlike Basilosaurus, Dorudon didn't undulate like a snake. It swam using powerful up and down strokes of its tail, just like dolphins and whales do today. This is a key evolutionary milestone. By the time of Dorudon, whales had evolved the swimming style that would define their lineage. Instead of twisting side to side like fish, they moved their spines vertically, powering themselves with their tails. This vertical motion is a signature of mammals. It's the same up and down movement you see when a dog swims. Whales simply adapted it for life in the open ocean. So by 40 million years ago, whales had completed the transition to a fully aquatic lifestyle. They were no longer tied to land. They gave birth in the water. They hunted in the water. They lived and died in the water. Their nostrils had migrated further up the skull, halfway toward the blowhole position of modern whales. Their ears had adapted even more for underwater hearing, with bony structures and fat pads channeling sound. At this stage, whale evolution had achieved something extraordinary, a complete transformation of lifestyle, anatomy, and ecology in just 10 million years. Think about that. From Pakicetus, running along riverbanks, to Dorudon, a sleek marine predator, was the span of only a few million years. To us, that feels like forever. But in evolutionary terms, it's a rapid, dramatic shift, one of the fastest and most clearly documented transitions in the fossil record. Let's step back and consider why this happened. Why did some land mammals give up their legs and return to the sea? The answer lies in ecological opportunity. The oceans of the Eocene were rich with fish, squid, and other prey. There were relatively few large predators compared to today. By moving into this environment, early whales opened up a whole new world of food resources. Natural selection favored those that could swim faster, dive deeper, and spend more time underwater. The success of Basilosaurus and Dorudon shows that whales had found their niche. But the story wasn't finished, because while these archaeocetes dominated the oceans for millions of years, they were evolutionary experiments. They were side branches, not direct ancestors of today's whales. Over time, they disappeared, replaced by new lineages that would give rise to the modern forms we recognize today. In the next phase of our journey, we'll see how whales diversified into two great families: the toothed whales, who mastered the art of echolocation, and the baleen whales, who became the largest filter feeders in Earth's history. Together, they would define the oceans for the next 30 million years, and ultimately, right up to the present day. By about 34 million years ago, whales stood at another crossroads in their evolutionary journey. Having conquered the oceans, their lineage split into two very different paths, one defined by sound, the other by size. On one side were the toothed whales, the ancestors of dolphins, porpoises, sperm whales, and orcas. These animals kept their teeth and evolved incredible hunting abilities. But their most revolutionary adaptation was echolocation. By producing clicks and listening for echoes, they could see with sound, navigating dark waters and hunting prey invisible to the eye. Imagine being a dolphin, swimming in murky coastal waters where vision fails. You send out a burst of sound, and instantly the echoes paint a three-dimensional map of your surroundings. You can tell the size, shape, and even texture of objects around you. A fish hiding in sand, a squid swimming at night. Echolocation gave toothed whales a superpower no other mammal had. On the other side of the split were the baleen whales. These giants took the opposite strategy. Instead of hunting individual prey with teeth, they evolved racks of keratin plates, baleen, hanging from their upper jaws. By gulping vast amounts of water and straining it through the baleen, they could capture swarms of tiny krill and fish. This was an evolutionary jackpot. By specializing in filter feeding, baleen whales could exploit one of the richest food sources on Earth: the small, abundant organisms that gather in dense schools. Natural selection pushed them toward larger and larger body sizes because bigger mouths could scoop more prey in a single gulp. Over millions of years, this led to the emergence of the largest animals ever to live. So by the end of the Eocene, whales had diversified into two lineages, the sound-driven hunters of the deep and the colossal filter feeders. This split would define the oceans for the next 30 million years. Whales are not just survivors in the ocean, they are masterpieces of adaptation. These creatures are living testaments to the power of life to transform, adapt, and thrive. Whether they continue to do so depends, in part, on us. Thank you for joining me on this journey through deep time. If you enjoyed this exploration of whale evolution, stay tuned for the next episode, where we'll tackle another evolutionary marvel.